Thanks for inviting me, and I'm here just to share some of the research that we have done on the modeling representations in speech normalization of prosodic cues by native and non-native listeners. So this is still, well, a work in progress, but we do have some results to share. So there is actually one of the fundamental problems, which is called the lack of invariance problem. It's quite interesting that all of the speakers might produce, say, all kinds of acoustic sounds, but for the listeners, they actually need to overcome all the acoustic differences in encoding the signals. So this can be a quite challenging problem to understand how listeners are doing it with all these kind of acoustic differences. So one of the well, possible things that people are doing is probably they have established some mental representations of speech sounds. So when they are judging the incoming signals, they can judge the signals based on their mental representations. So we're quite interested in, well, how we can model the mental representations. So there is a debate between the abstract and the episodic phonological representation. So for the abstractionist theories of phonology, well, researchers believe that the underlying representations are actually minimized, so they don't have a lot of details. And the phonological grammar can generate well, new kinds of forms. Well, there is also evidence showing that people do have this kind of abstract representations, but more and more studies are showing that well, it's possible that in our representations we do not only have those abstract representations, but we also include some details, especially the indexical details. Say when we are trying to store some sounds in our mind, we might have, say, speaker-specific kind of details. So that's pertaining to the talker's identity. So in speech perception, we also pay attention to indexical details. And we do have this episodic memory, so we're able to remember and recall a series of events, and that also help us in judging the new signals. So essentially, we believe that there might be some mental representations that we can make use of. And it's interesting to think that we might have different levels of the representations. We might have, say, representations with some details, and we also might have some levels which is more abstract. So how do we integrate this kind of representations? So we both need abstract representations and also have some details in the representations. So one of the ways to think to integrate these different levels is through parametric representations. So the idea is that we think of, well, when you're trying to create some mental representations, we think of it as when you're learning, say, when you're trying to process different acoustic signals through your life, you're actually creating some kind of distributions in your mind. So when you say interact with people in a speech community, you're trying to well, analyze the sounds, and you're trying to store the distributions of sounds, and you're constantly updating, say, some parameters of that distributions in your mind. So there is some hypothesis about the possibility of parametric representations. So we're quite interested in testing whether this is the case using tone perception. So there has been some models trying to explain, say, how we understand and normalize sounds. So one of the model is called the computing cues relative to expectations model. So in this model, well, we believe that, the researchers believe that acoustic cues are coded based on their difference from the expected values. So let's take a look at an example. I guess we all know that usually higher F0 would indicate voiceless consonants, and lower F0 would indicate voiced consonants. Well, if the talker is identified, so if you have some information about the talker, then it's probably much easier for you to decide whether this is higher F0 or lower F0. Say if the average F0 of a certain talker is 128 hertz, and then you have a coming signal of 154 hertz, then you know that this is considered as higher F0 than the average. So then you kind of expect that you have higher F0, and higher F0 usually indicate voiceless consonants. So then you can judge that probably the incoming signals are more likely to be a voiceless segment. So this is the model. However, we're interested in, say, what happens if the talker's information is not fully available. Say in the model here, computing cues relative to expectations, we do need to know, say, the average F0 of a certain talker. So we do need to know some information about this talker in order to make an informative judgment. But what happens if the talker's information is not fully available? And in one of the earlier studies we have done, we found that so even if you do not have talker's information, you are still probably able to make some judgment. So the judgment will be probably based on talker typicality, so how typical the talker is. So we would like to extend this study and to know more about the details of statistical distributions. So how we can make use of this idea of parametric representations of distributions in tone identification. So that's why we are trying to answer some research questions. So first of all, we're interested in whether native and non-native speakers use parametric representations of phonetic distributions in tone identification. So although there has been some hypothesis saying that there might be parametric representations going on, but we would like to think about a way that we can test whether there is parametric representations, and specifically whether we do have it in tone identification. And also we're also interested in whether if we kind of manipulate the population distribution and we create some kind of distributions that deviate from the original population distribution, what would happen? So would that affect identification by native and non-native speakers? So what we did is we started with tone identification using Cantonese tones. So maybe some of you are familiar with the Cantonese tones. We have these 6 tones where you probably would notice that we have some rising tones here, like the second one and the fifth one here. And then in addition, we have 3 level tones where we have, kind of high with 5-5 and mid with 3-3. And we also have 2-2. So if you would like to take a look at the 3 level tones here, it's represented in this figure. So we do have tone 1 here, which is the highest. And then we have tone 3 in the middle, and then followed by the tone 6, which has the lower tone values. So we decide to use these 3 level tones to test our hypothesis about the parametric representations. Because it's much easier if you think about it when you're trying to, say, estimate the distribution of these tones based on their F0 values. For these level tones, we only have, say, we only need to model well the height, right? So if we choose some rising tones, then we probably need to model both the height, and also we need to model, say, the slope. So we probably would need a bivariate kind of distribution. So that can be harder to model and harder to test. So we started with level tones first. So we do need to, first of all, have some ideas about what the distributions are in speech production. So we do need to know, say, what is the population distributions of these tones look like. So what we did is that we try to model the distributions of these tones from a Cantonese speech corpus. And we tried to choose 50 sentences produced by 68 speakers. Then we actually tried to fit a bunch of distributions, and it turns out that the skew normal distribution is probably the best fit. So it's a bit different from the normal distributions. If you're familiar with the normal distribution, we have 2 parameters. But in the skew normal distributions, we actually have 3. So we have the location, the scale, and the shape parameter. So we do need to find the 3 parameters in order to determine the shape of the distribution. So we tried to fit the skew normal distribution to our data. And we have, we tested, say, after fitting the distributions, we simulate the tones, the distribution of the tones again, and we compared the simulated distribution to the original ones, and we conducted some tests. And basically the tests would say that there is no difference between the simulated distribution and the original ones. So that means that we have a relatively good fit. So when we fit the data, so then we actually created 2 sets of stimuli because we have some knowledge about the distributions based on the corpus, right? So remember that we fit all the tones here. So we have some knowledge about the, say, the location, the scale, and the shape. So what we proceed to do is that we create 2 sets of stimuli. So one set would have the simulated distributions, and the other sets would have all the real stimuli. So we recruited another 34 speakers, and these speakers produced the Cantonese tones. And we also estimate the distributions of each tone produced by each speaker. So we do have some real stimuli, and in addition to that, we also have some simulated stimuli. So the simulated stimuli is based on the simulated distributions, because we do have the research questions whether, say, the listeners will pay attention to deviated, say, when you deviate the population from the original one, will the listeners pay attention or find, how should I put it? So they might be paying attention to the deviation or not. So as you can see that in these figures, we can simulate the distributions by varying the location parameter and the scale parameter. So by varying the location, you will see that the distribution can be moved to the left or to the right. by manipulating the scale, you would see that while we have different dispersion and the shape, whether it's skewed to the right or to the left. So we can manipulate these three parameters to give us different shapes of the distributions. And we're interested in whether listeners would actually notice the differences. So we recruited some listeners. Well, of course, we are interested in whether, say, the listeners would really have parametric representations. So whether they are sensitive to the changes of those parameters. And of course, we would include both native and non-native speakers. So we have included Cantonese as well as Mandarin speakers. And there is also one more problem that we need to do because of the tone merging phenomenon. So there has been some studies showing that there are tones that are merging, say, some speakers cannot really identify tone 3 versus tone 6, tone 2 versus tone 5, tone 4 versus tone 6. So we do want to make sure that we don't have subjects that are, they kind of merge these tones together. So we do want to do a pre-screening and make sure that at least, say, the Cantonese speakers can have the accuracy rate greater than 90%. So we don't choose those tone mergers. So after the pre-screening procedure, then we conducted an experiment on the two sets of stimuli. So we actually asked them to identify which tone it is among the three level tones. So if you remember from the previous slides, we have three level tones, tone 1, tone 3, and tone 6. So we asked them which tone it is from the two sets of stimuli. So one sets are the real stimuli produced by some speakers, and the other sets will be the simulated tones, basically based on the deviation of distributions we simulated. So first of all, let's take a look at the set that contains the real stimuli. So we do have the real tones produced by 34 Cantonese speakers. So we tried to apply a multinomial mixed effects model. We applied this model because we have three choices in the tone identification task. So usually if you have two, then you have a logistic mixed effects model, but we have three. So we need to use a multinomial mixed effects model. So we found that for both native and non-native listeners, the main effects of the parameters, location, and shape contributed significantly to tone identification. And interestingly, the scale effect was actually not statistically significant in tone identification for non-native listeners, but I think it's significant for native listeners. So at least we know that native listeners, their tone identification, where the parameters do contribute to their tone identification. And the next step is that we would like to fit a smoothing curve. So we have this locally weighted scatter plot smoothing curves. The reason that we would like to fit this curve is that we would like to see whether the listeners, say, in addition to fitting this model, to know that actually the three parameters are contributing to the identification. We're also interested in so the identification curve, essentially. So we wanted to know, say, as you can see in this figure, for example, if we have varied numbers of the location parameter, what would the identification curve be like? So originally we were thinking that probably we would have some peak areas. So that means this parameter occurs quite, well, is considered quite typical, to use layman language. So that means when you have parameters that's close to this value, then the identification rate of the tone would be quite high. So that means, well, if the curve looks like this, that means speakers do have some knowledge about whether a location parameter is kind of typical or not. So if you think about it, how do we prove that these parameters actually contributed to tone identification? Of course, we can just fit a, say, multinomial mixed effects model and test the main effects. But not only we're interested in that, but we also wanted to know if you change the parameters, if you change the, say, if you look at different values of the parameter, will we also have different identification rate associated with those parameters? So that's what we did to try to take a look at the identification curve with respect to the these values with these parameters. So let me probably, let's see if it's possible to draw here. Not sure if it's doable to, on Zoom we do have an annotations kind of, so you can draw on the PowerPoint. I don't really see a way of drawing here. So let me just describe it in words. So when you think about it, if, say, these parameters do not matter at all, then we would expect that the identification curve would be like a horizontal line, right? So because whenever, however you change these values, the identification rate actually won't change. So that means, well, basically the, say, the parameters of location will not really contribute to tone identification. Well, if there is, say, some changes that looks like this, so well, the curve goes up and down, then that means there are some optimal values in which, say, the speakers tend to make the judgment that this is the, say, the mid-tone, for example. So that means these parameters actually contribute to their identification. So that's what we did for both native speakers and non-native speakers. And it's quite interesting to know that for location parameter, there are actually two peaks. Well, we think that there are two peaks because, well, people do have knowledge about, well, both female and male speakers. So they know what kind of speakers are considered as typical male and also typical female speakers. So that's why there are two peaks for the location parameter. And we also did the same thing for the non-native speakers. It's quite interesting to see that they also have two peaks, but of course the values, say the peak values will be different among native and non-native speakers. And also, if you look at the shape parameter here, so compared to the native speakers, you do see a quite obvious peak here. But for the non-native speakers, we kind of see a relatively flat curve here for the shape parameters. So that means non-native speakers probably are less sensitive to this parameter shape based on the curve, their identification curve. So that's what we have found for the stimuli, for the one set of the stimuli, which is the real stimuli. And we also did it, we did the multinomial mixed effects model to the manipulated stimuli. So remember that we try to manipulate the distributions. We try to create different simulated distributions. We try to vary the location, scale, and shape parameters and created different distributions. So we also analyzed that experiment. And well, it's not out of surprise that again, well, the main effects of the parameters actually contributed significantly for both native and non-native listeners. So they probably do have some kind of parametric representations. So in addition to testing whether they have parametric representations or not, we were also interested in knowing whether, say, if you compare the tones that they identify as, say, the midtone versus the tones that they produce as the midtone. So we try to compare the pitch distribution of each tone produced by the speakers and the pitch distribution of each tone identified by the listeners. So we would like to see whether, say, the distribution of those tones produced by the speakers and those tones that identified by the listeners would overlap or not. So originally we thought that maybe the perception, the tones perceived and the tones produced, if you look at the distributions, they would overlap or they would overlap completely. However, well, when we did the analysis, we found that well, these two distributions, although you can see some overlapping areas, but well, none of them actually overlap completely. So that's for the native listeners. And similarly for the non-native listeners, if we try to plot the distributions of these tone values produced and perceived, still they do not overlap completely. So that's what we did. We were trying to see whether, say, listeners would kind of create a distribution that, say, reflects what the produced signals are like. But actually, these distributions do not overlap completely. So next, we're not only interested in, say, whether native and non-native listeners have this parametric representations or not. We're also interested in knowing, say, because in real conversations, you, well, seldomly just hear one word. So we do have a lot of contextual information available to us to help us perceive the tones. So we're interested in if, say, there is some contextual information available, will the contextual information influence our tone perception? I think this is already quite established that we do have some extrinsic effects. For example, if you, say, shift the F0 of the preceding syllables, say, 2 semitones upward, and then you asked the participants to hear and to judge the target word, then because the preceding syllables have been shifted 2 semitones upward, then they tend to hear, say, the midtone as a low tone. And well, similarly, if you shift downward by 3 semitones, then the target tends to be heard as a high tone. So that means if you change the environment, you change the contextual information, the syllables, well, surrounding the targets, then your judgment will also change. So that's not what we're interested in. We're interested in whether, say, you have contextual information, we want to know, say, when the contextual information is present, whether the parametric representations are still in force. So we would like to test two competing forces, the parametric representations and the contextual information. So let's consider a situation. Well, there are two forces. First of all, we have the parametric representations. Well, you can think of it as we kind of have knowledge about what kind of tones would be typical, say, for example, will be likely to be perceived as a midtone. We have this knowledge in our mind. This is due to parametric representations because we have knowledge about the distributions of these tones. So that's one force, and the other force is the contextual information. So say if we have some speakers midtone, and this midtone falls within a typical midtone range. So this is what we have designed to test the two forces, because if you want to test whether parametric representations and contextual information say they're competing with each other, so whether one, say, factor parametric representations will not be effective if there is contextual information present. So we try to create this kind of situations to test how these two forces compete with each other. Say if there is a speaker A's a midtone, and this midtone, according to your parametric representations, you know this tone actually falls within some typical midtone range. So that means it's a typical midtone. Then if we only have parametric representations, we only make use of this parametric representation to identify the tone. We will identify it as a midtone because it's a typical midtone. However, if we provide some contextual information, say we create a tone, that would be, say, a high tone. For example, we create some high tone as if this midtone should be a low tone. Then if you look at the contextual information, this tone should be perceived as a low tone instead. So that means the two forces are in competition. So whether if you rely on, say, totally on parametric representations, you rely on the knowledge whether this tone is typically mid or low, then you would say this is a midtone. However, if you consider totally on the contextual information, you would say that this is a low tone. So we kind of just design this kind of experiments to check whether speakers are using parametric representations or they're using contextual information, or they're using both. So what we can do is that we need to obtain well the so-called the typical midtone range. So we do need to find out what is this typical midtone range. So what we did is we created, we actually tried to find the optimal pitch range based on our previous experiments. So we tried to figure out this optimal pitch range for the female voice and the male voice. And then we need to introduce a function which is called an indicator function, because there might be different situations. Say that there might be values that do not fall within this typical tone range. So that's why we need to create an indicator function. So basically, it means that this function can represent whether tone value falls within the optimal pitch range or not. So this function is defined like this. If the F0 values presented in the embedded sentences well, has the f0 values that fall within the optimal pitch range, then the indicator function would be equal to 1. Otherwise, the indicator function will be equal to 0. So if we have a value that falls within this typical mid-tone range, then we have a 1 for the indicator function. And if it doesn't, then the indicator function has a 0. So we can test whether the indicator function, say, is significant or not. Then we would know whether speakers are still using knowledge or they're using their parametric mental representations in perceiving these tones. So, so interestingly, well, of course, when the sounds fall within the mid-tone range, the typical mid-tone range, it's more likely that the speaker would think of it as a mid-tone. So that means parametric representation is still it's still working when you have contextual information. So we do have these two forces are still competing with each other. So it doesn't mean that if the contextual information is present, then we don't have the parametric representations at all. We don't use parametric representations. It means that we would use both. Of course, this contextual information is limited in our design. We only have some high tones and low tones. And it's possible that if you have a complex contextual information, if you have a whole sentence there, then the contextual information might be playing a more dominant role, but we haven't really tested. So that's one possible outcome, that if you included, say, more tones in the contextual information, then the speakers might be using the contextual information more compared to the parametric representations. So you can think of parametric representations as kind of a prior knowledge that speakers have stored in their mind. So we did find that, say, the both contextual information and the parametric representations play a role in tone identification. So based on these results, we were trying to introduce a new concept, which is called the probabilistic parametric representations. The idea is that, well, based on the experiments, you can already see that we have tested our hypothesis by showing that these three parameters, the location, the scale, and the shape, these parameters, they contributed significantly in tone identification, at least for native speakers. So some of the parameters might not be contributing so much for the non-native speakers. So that means at least the native speakers have this parametric representations. So that means they can store distributions in their mind, and they have some knowledge about the distributions. So in addition to that, we would like to propose the idea of probabilistic parametric representations. So that means they would know, say, what kind of parameter is more typical parameters. So among all of the speakers that we presented to them, say among the 34 speakers, we extracted all the location parameters, the scale and shape parameters, and we try to plot this identification curve. And it's not a flat line. So that means they do have knowledge about how likely the parameter would be among the speakers in one speech community. So that's what we found. And we're also, well, we also have some findings about the non-native speakers. And well, for the shape parameters, it seems that it doesn't really show a big change in the curve. So the non-native speakers may not really have, let's say, the whole picture of the probabilistic parametric representation. So they might not be very sure what kind of values would be typical or not for some speakers in the speech community. So that's the well, one of the biggest findings for the current study. And of course, we also found that if you deviate, say you created some simulated population distributions with deviation, then it will actually affect tone identification for both native and non-native speakers. And although, say, the distributions of estimated, the distributions from the production and the perception overlaps, but well, neither can native or non-native speakers establish the representations, say, exactly the same from the production. So the distributions that you see in the plots do not really overlap completely. And for the experiments testing the two competing forces, we do find that the parametric representations of phonetic distributions are still in use when we have the contextual cues present. So that's our findings, where we have already published the results for native speakers, but for the non-native speakers, we are still working on the paper, but well, I'm actually showing you the results that we have for the non-native speakers. So that's pretty much what I have for today. Thanks for listening. Any questions or comments?